Okay, last way we're going to see how to calculate the change of enthalpy of the reaction. 1 mole of carbon gas plus half a mole of oxygen gas to make a mole of carbon monoxide. This time the information we're given is that the Gibbs formation of carbon gas is 671.257. I'm positive that's got to be, that's got to be a positive value because it's not favored for carbon to turn into gas. When Gibbs is negative, it's a spontaneously occurring thing. When Gibbs is positive, it doesn't happen on its own. So I've got this big positive number for forming gas, carbon gas, from carbon solid. And I know my diamonds don't just turn into gas. So, confident. Okay, carbon monoxide. When you make a mole of carbon monoxide from its elemental parts in standard state, it happens spontaneously. And that is negative 137.168 kilojoules per mole reaction. So you can write down those values and do that calculation with me. I'm given the Gibbs values, and let's write down the entropy values that were given as well. Entropy of formation of carbon, write down 158.096 joules per mole Kelvin. The entropy of oxygen is 205.138 joules per mole Kelvin. The enthalpy of carbon monoxide, 197.674 joules per mole Kelvin. Okay, so you could try to solve this. Pause. And now I'll show you, because you hit play again. So, I know that I have these Gibbs values, I have these entropy values, and I'm looking for enthalpy. So I'm going to use this equation. Delta G equals delta H minus T delta S. So let's solve for the change of Gibbs of the reaction first. Change of Gibbs is going to be the Gibbs of formation of the products minus the Gibbs of formation of the reactants. Okay, so delta G of the reaction equals the Gibbs of formation of the products. I'm forming carbon monoxide, so that is negative 137.168 kilojoules per mole of reaction. Okay? So Gibbs of products minus the Gibbs of the reactants. And the reactants I have are carbon gas, and to form carbon gas, that's going to be 671.257 kilojoules per mole of reaction. And I'm also forming half a mole of oxygen gas, but I'm forming it from oxygen gas, so the Gibbs of formation of oxygen gas from oxygen gas is 0, right? So 1/2 times 0. I'm just going to leave that as it is. Okay. So my Gibbs of reaction is going to be negative 137 minus 671.257, and I get a Gibbs of negative 808.425 kilojoules per mole of reaction. Alright, then I can also solve for the entropy of the reaction. I'm going to use the equation. You find both of these equations, by the way, in this equation too. They're all on your Gregor sheet, so that's cool. If you get stuck and you see things that you have, you can actually tie them together and see how to use them. Change of entropy of a reaction is the entropy of the products minus the entropy of the reactants. Notice you're not saying how much is the entropy change when you form things, because everything has a certain amount of possible arrangements. So we really just measure how many possible arrangements or how much entropy each element has, or each element, each compound has. And we'll get the difference between these. So how much is matter becoming more organized or less organized? So change of entropy of the reaction equals entropy of the products, 1 mole of carbon monoxide. That is 197.674 joules per mole Kelvin. Okay, minus our products. Our first first reactant. It's going to be carbon gas. So 158.096 joules per mole Kelvin. Okay. Plus, put in a double parenthesis, plus 1/2 of a mole of the oxygen. So 1/2 of the entropy of oxygen is 1/2 times 205.138. joules per mole Kelvin. Okie doke. So now I have 197.674 minus the 158.096 plus half of 0.1588. So be sure that you add 158 plus half of the 205 first, and then go 197 minus whatever you got for this total. And you should get, your entropy is a negative 62.99 joules per mole Kelvin. It's really mole of reaction Kelvin. Okay, so we have our change of entropy, we have our change of Gibbs. We're going to plug them into these guys. We'll plug in the temperature and we'll get the enthalpy. Notice I have all these not values. That's that big degree sign thing right up here. That means all of this is happening at 25 degrees Celsius or 298 Kelvin. So I know my temperature too. Okay, here's my Gibbs. Here's my entropy. I'm using delta G equals delta H minus T delta S. I'm solving for delta H, so let's get it by itself. We'll add T delta S to each side, plus T delta S. Alright, so I end up with delta H, so all I have here, is equal to delta G plus T delta S. Let's plug some stuffs in. Delta G was negative 808.425. Kilojoules per mole of reaction, plus T delta S, so plus 298 Kelvin. It has to be in Kelvin because this guy is 62.9 kilojoules per mole reaction Kelvin. Oops. So my temperature times my entropy, 62.99 joules per mole Kelvin. Okay. But here's the problem. I don't want to add kilojoules plus joules. That's just weird. So I'm going to turn these joules, or sorry, these kilojoules into joules. Wow. So I'm going to divide by 1,000. 1, 2, 3. Okay. So really it's going to be negative 0.06299. Okay. So a negative 0.06299 kilojoules per mole reaction Kelvin. Alright. So that times 298 added to our Gibbs, and when you type all of that in, guess what it equals? You might have guessed right. Negative 827.196. Let's do some rounding, right? I actually have to look back at my data and see what sig figs I had. Let's see. We only used 3 sig figs for the temp, by the way, 298. Really was 298.15, but right there, that limits us to 3. Everything else had 5 or 6, so bad form. My bad. I should have used 298.15, and then I would have had 5 sig figs. But I used 3. I get 3 sig figs. Equals a negative 827. That's what I got. And that is kilojoules per mole reaction, and it's awfully familiar because it's the same value we got using all the other methods. Plus, and by the way, the AP test often gives you what temperature to use, so you'll know how many sig figs, so no worries about that, right? It'll say 298.15 or it'll say 298, so no worries. Our values make sense. It's a really good thing to calculate and then ask yourself, like, is that reasonable? So entropy values usually are in the joules. Gibbs values are usually in kilojoules. And when we look at this, I have a negative entropy, and I've got 1 mole of gas plus a half mole of gas turning into 1 mole of gas. I'm decreasing my moles of gas. I should have a negative entropy. I'm only decreasing by half a mole of gas, so that's 62. That seems good. For my Gibbs, carbon gas is not stable. Like that's, yeah, to turn carbon gas into other stuff, it's going to often be favored, would be favored. And carbon monoxide is something that is stable in our room and it exists, so there's a good chance that, like, yes, this is going to be a spontaneous reaction, and anything that's spontaneous, it's going to be negative Gibbs. Cool. And sign-wise, it makes sense too, because we have this exothermic thing with it's like hugely exothermic, right? Negative 827 kilojoules, the small unfavored entropy, and overall, it is a favored Gibbs. So you can see the Gibbs is taking into account that the enthalpy, it's mostly enthalpically driven, because the enthalpy is so large and negative, and then you have this small unfavored entropy. So just to throw in some of that. Hope that helps, guys.